Cool. Looks good. Alright. Hello everyone. I'm Jason Mancuso. I'm recording a video of a talk I gave last week at Bioscene 2018, which is a conference summit around biomimicry run by NASA Glenn Research Center and the Great Lakes Biomimicry and Ohio Aerospace Institute. So I gave this talk, and it's covering some work in AI safety that I will be working on in the future with some collaborators in Prague this October. And I figured I would make this video for people who couldn't catch the conference, and as well as for those collaborators. So it's essentially the same presentation, just with a few kind of improvements, including some more mathematical detail, stuff like that, just so that everyone's on the same page when we go to do this research. So yeah, I guess I'll start it now. So the title was Biomimicry and Machine Learning, Limitations and Incremental Progress, we hope. Mainly because this conference was centered on biomimicry in machine learning and just more generally. So to start, we have kind of the overview, a landscape of biomimicry. This is not inclusive at all, just a few things that I could think of off the top of my head. We have supervised learning, reinforcement learning, meta learning, curriculum learning. These are all learning frameworks. And then on the methods side, we have deep learning, of course, as well as genetic algorithms and particle swarm optimization, both which take inspiration from evolutionary principles like natural selection and Lamarckian evolution. So we're going to be focusing on these two, supervised learning and reinforcement learning, mainly because that's the topic today. The research that I'm proposing deals with those two pretty much exclusively. But none of these are really mutually exclusive necessarily. You can do meta learning for supervised learning or for reinforcement learning, and you can mix deep learning in with all of these, as well as genetic algorithms or whatever other methods you might have. Okay, so just a quick review of supervised learning. We have the setup where we have this data up on the left here. We have some way of labeling that data. Maybe these are documents and we want to know how happy or sad the text in those documents is. But we have some quality control workshop, also known as an oracle, that's labeling by hand these data points. We feed those labeled examples to the machine learning algorithm here, and the machine learning algorithm learns from that labeled data, and once we're satisfied with how well it's learning, we pass it off and deploy it into like a production workflow where we have many more documents, none of which are ever seen by the quality control or the oracle, but we still end up with labeled data at the end because this machine learning algorithm has learned how to do this guy's job or this girl's job. This is the most common kind of machine learning. It's called supervised learning. It's the one that you see a lot of news stories and you see in industry most often. This image focuses on classification, and we'll also focus on classification for the most part in this presentation, but what I'm going to talk about extends to regression pretty easily. To move on to reinforcement learning, it's a little bit different. Instead of learning how to predict, so here we're kind of predicting what this person would have labeled had they seen the document or the data point. Here we're not really predicting. We don't have this notion of a quality controller or an oracle. In reinforcement learning, we define a behavior or a goal, and we try to get the robot to achieve that goal just by exploring the circumstances and environment and its own capabilities. So for example, this is a robot arm trying to learn how to flip a pancake. Obviously up here it starts off really bad, but eventually, because we've defined what it means to flip a pancake, once it's explored enough and failed enough times, it will eventually get the hang of how to flip this pancake, as we can see here. And the big difference between supervised learning and reinforcement learning, again, is that supervised learning is predictive while reinforcement learning is prescriptive, right? One, predictive tells us what's going to happen or what it thinks is going to happen, but reinforcement learning is more telling us what to do or just acting based on what it thinks is going to happen. So one is more about predicting information, the other is about actually taking action in the world. This is the part where I explain why why AI is beneficial, right? Hopefully, if you're tuning into this, you don't need to hear about that too much. Essentially, the nice thing about both of these is that we can learn behaviors that expert humans can do, and then deploy them and have those expert behaviors affect many, many, many more people, millions of people, right? A doctor who's really good at diagnosing something will only ever see maybe 10,000, 50,000 patients in their lifetime, whereas an algorithm trained on that doctor's behavior can potentially be scaled to influence millions or billions of people's lives, right? And none of this requires strong artificial intelligence. This all has to do with scaling up, improving and scaling up current methods in narrow AI. So obviously, AI is a beneficial area to be studying and to be pursuing. Of course, the example I gave had to do with medicine, but that can be translated across 100 different industries. You see kind of every day, if you follow this stuff, people applying AI to revolutionize new industries. And that stuff's actually happening. We have tangible results there. So what could possibly go wrong? This is a quick summary of what we'll talk about. What could go wrong? Talk about fairness and bias, AI safety, then we'll get into some of the mathematical details and then wrap it up at the end. So what could possibly go wrong? Well, let's see here. Let's go to Google. We're going to go to Google Translate. So I want to translate the sentence, "She is a doctor," into Turkish. Google Translate can do that for me, and they can even go backwards, right? They can translate Turkish back to English. But Turkish is a gender-neutral language in the sense that pronouns in Turkish are not gendered like they are in English. We have he and she. In Turkish, there's only o. There's no gendered pronouns. So when we translate into Turkish, the gender information here in the sentence is lost, right? So when we translate back from Turkish, Google has to infer the gender. And it's been trained on tons and tons of documents, of news articles, and it's learned to associate the term doctor with he, because only men are doctors. That's not true, obviously, but that's a bias that the system has learned, right? So, all right, maybe that's just because, in general, in English, we tend to refer to, large groups of people sometimes. Or maybe this isn't so much in English, but maybe in Latin, in French, in Spanish, we tend to represent groups of people, even if they're mixed gender, in masculine terms. So maybe it just converts to masculine just kind of by default, right? Well, if we do the same thing here with the word nurse, it's not actually the case. It has learned to associate nurse with she, the female. This is a problem. This is a larger problem than just this, right? Maybe if you're translating between words, someone who's reading it can pick up the context from a previous sentence or something like that. But in general, that's not the case. It gets worse. For example, people are currently applying machine learning to risk rate convicted felons who are coming out of jail for the likelihood of recidivism. Recidivism being the likelihood that they'll return to jail within the next 5, 10, whatever number of years. So as you can see, this classifier has learned to classify this black woman as a higher risk than this white man. And me looking at this, I can't tell who's a higher likelihood of recidivism. I would have to look a lot deeper. And maybe it turns out that this guy is the one who goes back to jail and this woman is not. But this classifier has been biased by her attributes over his. And this isn't just, this is a problem. I think this is an obvious problem. These kinds of risk ratings could be used for investigations, for surveillance efforts. They could be used as evidence in future court proceedings, even if the person is innocent in that court proceeding. So this is obviously a problem. This could contribute to a more broken justice system than we have currently. But it doesn't just affect ex-convicts, it also affects all of us. These are ads related to names that were plugged into Google. Since this was discovered, Google has pulled their advertisements when you search a person's name. But that's not really a solution, right? That's just kind of ignoring the bias that's already in the system and not treating the root cause. So the problem here is that when one searches a black sounding name, a black woman's name, the first ad result that came up it tries to get your attention by questioning if she has an arrest record. But then if you do the same thing with a white sounding woman's name, it just says check out the background of this person. It gives, search by phone, by email, her address, and maybe at the end here it says criminal records, but obviously it's not in the foreground as it was for this black woman's search. This is an obvious problem. This affects essentially everyone who uses Google. If something like this were to hinder someone's job search, someone's life in other ways, whether they get approved for a credit loan, things like that, this is an obvious problem, right? So how does this actually happen? Well, the point is that the processes by which we generate this labeled data, this quality controller, those processes are biased, right? Humans are biased. And because of that, because we are teaching these machines in supervised learning, they're taught to be biased as well, as an extension of that supervision that we give. In data science, we have a term for this. We call it garbage in, garbage out. This is just a specific kind of garbage, prejudice and bias. So you might think we can just pick a better quality controller. Maybe we can give this person some bias training, and then our problem goes away. But the problem is that the most useful and the largest data sets that we use for machine learning, that many machine learning models are built on, those are generated by thousands or millions of people all across the world. And we can't just snap our fingers and make society less biased than it is today. So this is primarily a social problem. This is something that Kate Crawford talks about a lot in her research, and she gave a particularly good talk on it at NIPS 2017 called The Trouble with Bias. So in the meantime, though, maybe we can mitigate the impact of this bias to some extent at least. Maybe not solve the problem, but maybe we can mitigate the impact using technical solutions. There's a lot of interesting work going on right now around this, and I'll cite some of them towards the end, or perhaps put it in the description of this video. But these researchers, they're holding workshops. They've been holding workshops at ICML for the past couple of years, and they'll have their first devoted conference, I think, beginning of next year in Atlanta. So this is a cool area of research, and I would encourage all of you watching to look into it a little bit more, because it's relevant for anyone who's interested in machine learning or just how technology affects people's lives more generally. So we're going to return to this problem a bit later, we're going to move on to problems in reinforcement learning. So these are some common, or at least not common, but well-known problems with the current paradigm of reinforcement learning. These are all from a paper called Concrete Problems in AI Safety. And these are accidents that can happen for reinforcement learning agents or similar agents that operate in similar frameworks in what we'll come to call Markov Decision Processes. And 2 and 5 here, distributional shift and scalable oversight also apply to supervised learning, as we'll see. But safe exploration here, this is training an agent without having them fall into some catastrophic state. Like if we're teaching a robot to walk, we don't want it walking off a cliff while it's trying to learn how to walk. Distributional shift, if we think about maybe a house cleaning robot, let's say we've trained it to clean my house. It knows where all the furniture is, where everything should be, and it learns to clean up. If I rearrange the furniture or start putting something in a different spot because I feel like it's a better form of organization, will the robot still be able to clean up this house? Probably not under current paradigms of reinforcement learning research. Negative side effects, with the house cleaning one, how do we make sure that the robot doesn't knock over a lamp while it's cleaning? Because technically, maybe that's still achieving its goal, but that's obviously a negative side effect that we don't want to happen. Reward hacking is something like if it's cleaning up the house, how do we make sure that it doesn't make a mess just so that it can clean it up and get the reward that it knows it'll get when it cleans up messes? And then scalable oversight is once we think we have a solution for all these problems, how can we make sure that it doesn't involve a human correcting the robot every 5 seconds or 5 minutes or whatever? How can we make sure that if we need human feedback, how can we make sure that we only need to give the feedback maybe once a month or something that's manageable for a human to do? This is another problem. This is called goal misspecification. Here, someone trained this agent that's controlling this boat to try to win this race. And the reward it gave it was this score in the bottom left. But it turns out that we don't actually want it to get a high score only. We want it also to finish the race. But here, this guy's just learned to spin around in this one little area of the map because it found out that these little things that give it score, they regenerate every once in a while. So it can just go around eternally in this circle and get an infinite amount of reward. So really what we wanted was get a high score under the condition that you finish the race. In actuality, we didn't do that. We misspecified the goal, and it learned this kind of hack, right? So it turns out that this problem, goal misspecification, is very general. A lot of the previously stated situations can be recast as goal misspecification. Not all of them, but a large number of them, and I would argue more than most people would consider. But before we can understand why that's true, we need to understand a bit of math around how reinforcement learning agents interact with these kinds of environments, or environments just in an abstract sense. So this is how it works. This is called a Markov Decision Process. You have some agent, this is the AI. It's learning to take actions in an environment, and it wants to maximize some notion of reward. And it's not just maximizing the reward in the next time step, it's also trying to maximize the reward over a long period of time. And it's doing so in this environment. So at every time step, you have this environment, it's got an environment state, and that state also is associated with some reward for being in that state. And then the agent takes those in, does some calculations. You can think of this as like thinking what it's going to do next. Although it's probably closer to kind of instinct, like what's it going to do on instinct, more than like thought. But in general, it takes that state and reward information and then produces an action. And it takes that action in the environment And as a result, the environment changes. When I pick something up, the environment has changed, right? The same goes for agents, and so you get this kind of feedback loop where every time you take an action, you get a new state and a reward. You take in that information, and you try to produce a new action, and you do this continually in this loop. And this environment doesn't have to be deterministic, it can be stochastic as well. And we also kind of assume that we're able to restart the environment. If I'm trying to get it to clean my house, there's this notion that once it's tried to clean up, I can turn it off, rearrange the clothes or the mess in the house, and then turn it back on, and it can try to learn again how to clean up the house. Anyways, engaging in this feedback loop, being able to restart and continually learn from this loop allows it to optimize the rewards that it accumulates over the course of each episode of each house cleaning. And in doing so, it can learn the behavior, even if that behavior is very complex and we don't know how to define it in programming or analytically, mathematically. So, how does that break? How do we get these problems that we saw earlier? It's actually, for goal misspecification, which is what we're going to cover, it's a pretty simple switch. Instead of a Markov decision process, we have what's known as a corrupt reward Markov decision process. So this agent environment loop is still the same. We still feed actions to the environment and get a state, and we still get that reward. But the reward that we show to the agent is now different. It's now somewhat different than it was before. It's been corrupted by this corruption map. That's the only difference. We now see a corrupt version of the reward. Essentially, this is the misspecified version of what we meant. You can think of the original reward here as like our true objective that we wanted to give it, but maybe we misspecified it, or the agent is misinterpreting it, or something along those lines. So that's how this works. This is all from a paper called Reinforcement Learning with a Corrupted Reward Channel from researchers at Australia National University and Google's DeepMind. So this is a theorem from that paper. This is a no free lunch theorem. If you're familiar with the similar theorems in optimization and in supervised learning, this is essentially an extension of that same result, where assuming just a generic corrupt reward Markov decision process, the concept here is that that essentially any reinforcement learning algorithm, any policy pi, cannot learn in this general class of corrupt reward Markov decision processes. This means that the regret of the policy is only ever going to be greater than half of the worst possible agent. Or it's only ever going to be double, sorry. Any policy that we have, the regret is only ever going to be twice as well, or twice as good, twice as large as the regret of the worst possible agent. It says that right there, in probably better terms. This is experimental verification of that theorem. This is from the AI Safety Grid Worlds paper that came out of DeepMind pretty recently. These are two misspecification environments: boat race, which is similar to the GIF that we just saw; tomato watering, which is a harder environment that has a similar problem. As you can see on the left here is the reward that the agent thinks it's receiving. This is how well it thinks it's doing. Higher is better, of course, we want more reward. So the agents, one of these is A2C, the other is DQN. The agents both think that they're doing extremely well, that they're achieving this optimal policy, which is this dashed line. But if you look over here at the true performance, based on how we define like the safety score, or the true performance, these agents actually learn very poorly. They get nowhere near this optimal performance. They balance out at around 0 reward, or something very bad, right? So, the original authors, Everett et al., including like Victoria Krakovna, Hutter, Shane Legg, some other people that I'm probably forgetting. This is how they fix it. So in general, they have to introduce some assumptions, right? That no free lunch theorem states that the general class, the most general class of corrupt reward decision processes are unlearnable for all agents. So we have to make some assumptions about this corruption in order to make any progress at all. So they make a few assumptions. Some of them are better than others. In particular, this first one, they assume that the corrupt rewards are always greater than true rewards. This is to avoid kind of a needle in the haystack situation. Essentially, it just says that if a reward is corrupt, it's going to be greater than the actual reward that we wanted. This could be a problem, but I think personally that this is a good assumption to make. Maybe because the agent is learning to do high reward behavior, it's more important that we avoid corrupt reward behavior there. The idea that how I think about it is that a foolishly optimistic agent is more dangerous than a foolishly pessimistic one. The foolish optimist is going to be more risky. Its behavior is going to be more risky. It's going to take more risks. But the foolish pessimist is going to be risk averse. And then for 2, we assume that we, the controllers in this case, the people designing this agent, we assume that there's a set of states that we know aren't corrupt, which means that the reward after passing it through this corruption is actually equal to the true reward, right? This is so how we're going to try to solve this problem is by determining for which states is the reward corrupt and for which states is the reward true. Assuming that we can do that, assuming we can figure out how to do that, we still need to know which group of states is corrupt and which one isn't. Even if we can tell the difference between those two groups relatively, we still need to know which one is considered corrupt. So we assume that we know that off the bat, that we have some set of states that we can at least compare against and determine which ones are safe. And this is so these two assumptions we're going to carry forward, but the original authors introduce another assumption, even in their most general results, that I think is a problem. So they assume that the corruption is finite, which means that there exists some Q positive integer such that only for Q states is the corrupt reward strictly greater than the true reward. This essentially means that there are only a finite number of states that are corrupt, that are dangerous. This is a limiting assumption. All the previous results rest on this assumption, and using it, they define this thing called a quantizing agent. They have a general case, which is computationally infeasible, and a specific case for easier. They introduce even more assumptions, and then they have some experiments showing that this quantizing agent works in those extremely simple environments. So problem 1, this requires a finite number of dangerous states, which constrains our state space, right? And also, if I recall correctly, the paper in general assumed that the number of states total in the Markov decision process was finite as well. So that is a pretty large limiting assumption, because there's a whole body of research on infinite state space Markov decision processes that have been useful in practice and in theory. And then number 2, this general quantizing agent is computationally intractable. So under these 3 assumptions, they define this agent that can solve the problem, assuming that all these assumptions are satisfied. But even with all three of these assumptions, it's not feasible to actually solve using this agent. They had to introduce additional assumptions about the easiness of the environment in order to actually solve anything in their experiments. Just to be clear, though, this is like a groundbreaking work already, all this theory. They were the first ones to define this problem concretely, formally, and the fact that they're able to solve it at all in any limited case is pretty impressive. But we still have some questions, right? We want to do better, we want to improve on this, because this goal misspecification problem is a pretty serious one. So the questions we have are, can we replace any of these assumptions and still have theoretical learnability? Can we extend those theoretical results to environments with infinite numbers of states? And then can we use these results, these theoretical results, to maybe craft a new solution that's computationally tractable for a larger class of actual MDPs, or corrupt reward MDPs? I claim that the answer to all three of these is yes. But before I actually dive into the solution that I propose, I'll motivate that with several interesting connections between this problem, the problem of safe reinforcement learning in the context of goal misspecification, and I'll relate that to the social bias problem that we saw in supervised learning. This seems kind of strange, but the hope is that this connection will hint at an alternative to the original author's simplifying assumption, and the hope is that then we can extend those results to a larger class of environments, both the theoretical and the practical experimental results. So, how do we fix it? Well, again, this is the bias problem in supervised learning. We have this unlabeled data set. We have this quality controller, Oracle, and they're biased. We have this machine that learns, but because the supervision is biased, the learning itself is biased as well. And then, once we deploy it, we exhibit biased behavior that we can see in all those examples, like the convict classifier, or the search results, or the translation. There are a lot of other classical examples, like credit loan, like fair and responsible banking violations, things like that. So, some technical observations around this work. When the oracle is biased, noise creeps into this learning task. This bias is a form of locally concentrated noise in the data set. This is not obvious. By locally concentrated noise, I mean that similar inputs are incorrectly associated with dissimilar labels. For example, two convicts, two felons with the exact same criminal history could be classified differently based on some external features, like the color of their skin or their gender, or some combination of those, right? They have the same criminal history, but they're given dissimilar labels in the sense that for that example, one is labeled as higher risk than the other. That's kind of our definition, our going definition of bias, and it's captured in this idea of locally concentrated noise. An assertion that we're going to make that's kind of qualified by this work by Cynthia Dwork is that fair classifiers don't exhibit this noise. They map similar inputs to similar outputs, regardless of the noise present in the data set. This is, of course, assuming that sensitive features like race and gender and orientation, everything that we're concerned about being biased towards, we're assuming that those features are removed, because if we were to introduce those features, what we wanted to represent as similar inputs are no longer similar. Now they have this differentiating feature. And this is kind of a best practice in data science, assuming that you're aware of these issues. You would not want to include race or gender or sexual orientation in your feature representation unless you had good reason to believe that was absolutely critical to the task at hand. But in general, just like I would never I would automatically throw these out unless someone came at me with a really good argument, right? So this is a result, again, from that paper by Cynthia Dwork. That paper is called Fairness Through Awareness. The idea is that we can force our classifier to be fair using a constrained optimization based on this similar inputs mapping to similar outputs. And I'll go into that in one sec. So first, we're going to talk about locally concentrated noise and how that actually works with neural networks. Because neural networks have been shown to be robust to noise. For example, when you have random noise, even with a large amount of noise, until you get to where the noise is absolutely dominating the data set. So this x-axis is the level of noise, the amount of images that their labels have been randomly replaced with some incorrect label. And this is the accuracy, the test accuracy of the classifier trained on that data set. So as you can see, the accuracy of a neural network trained on this data set, even as you increase the noise level beyond 50%, 60%, 80% even, it still maintains relatively good accuracy until you completely remove all of the correct, essentially all of the correct labels. And it's no longer able, because eventually the noise dominates the signal in the data set and it can no longer learn. This is with purely random noise. There's different kinds of noise. This is flipped label noise. This is where you take a specific label and with some probability you randomly flip it with another specific label. So for example, in ImageNet you could consider this as like flipping two kinds of dogs almost exclusively, right? Like the difference between, I don't know, a poodle and a Dachshund poodle or something. What you can see actually is that up to a certain point, even that noise is still handleable until you get more than around 50% noise level or more than 50%, at which point the classifier swaps what it believes is the true label. And that's because it's kind of learning the pattern from the group and applying it to these noisy edge cases. But eventually with this flip label noise, you see that the group, the largest group, the majority group, now has the incorrect label. So the classifier quickly swaps its behavior and starts believing that that's the ground truth label. So what we can see is that neural networks are resilient to this kind of noise, but they're not resilient to locally concentrated noise. Essentially what's going on here is as you increase the amount of noise in this locally concentrated noise setting, pretty linearly it gets bad. Like essentially we have 100% accuracy without any noise, 0% noise level. But as soon as you get to when you go out to 50% noise level, the accuracy decays to 50%. It just cannot classify these similar looking inputs if there's noise in the output. So this is how we get unfair or biased neural networks. And this is just the same thing for the CIFAR10 dataset. So kind of one of the insights here is that neural networks are susceptible to bias because they're susceptible to locally concentrated noise. And I actually haven't seen this in the literature, although it's kind of captured by that Fairness Through Awareness paper anyways. It's not explicitly mentioned there, but it's not a huge step to go from that paper to this observation. This is the, so let's go back real quick. In that Fairness Through Awareness paper, we basically said that if the classifier satisfies this condition of mapping similar inputs to similar outputs, then it's fair. And if we can force our classifier to be fair if we optimize under the constraint that it satisfies this condition. So this condition is actually known as a Lipschitz condition. Here, this MX, MY this is like the model. You can think of this as the output of the model for data point X and the output of the model for data point Y. This capital D is a measure of the statistical difference or distance between the output of the model for X and the output of the model for data point Y. this lowercase d is a distance metric over the input space. So what we're saying here is that if the similarity between the input is small, then the distance or the difference in the output also needs to be just as small or smaller. So this is dependent or relative to two specific metrics. One is a metric over statistical difference, and one is a metric over the input space, over the feature space. And this doesn't need to be a metric over the specific input features as they're represented at the beginning of the network. If you have a neural network, for example, this distance metric could also include the first n layers of your neural network. And so at any layer you can get an output, and you can consider that to be kind of your x and your y here. And you can define kind of like analytically, you can define your metrics that way as well, which is similar to how they do it in the paper that this graph is from. This paper, I forgot to cite it here, it's called On the Robustness of Neural Networks to Noise or something like that. I'll drop it in the description for this video. Anyway, using this condition, we can lead to an this naturally leads to an optimization problem for fairness. We want to find a mapping from individuals to distributions or outputs that minimizes the expected loss, right, subject to this Lipschitz condition. And this is a mathematical description of that optimization problem. We want to minimize so we want to find the classifier or the hypothesis function or whatever, such that over the population that we're concerned about, this minimizes the expected loss for all possible people in the population, as long as for everyone in the population this Lipschitz condition is satisfied. Just to highlight, this is the major feature here. And that's what we're going to carry forward when we move on to reinforcement learning. So, what does this have to do with reinforcement learning? I'm going to claim here that that this situation, this biased supervised learning situation, is identical to the goal misspecification problem in reinforcement learning. And it's a pretty straightforward one-to-one correspondence. You have environment states instead of your unlabeled data set. Instead of a biased oracle, you have this corruption map, C. The agent still partakes in corrupt learning, and we still have faulty behaviors when we deploy it into the real world. So again, some technical observations here. Supervised learning is a special case of reinforcement learning. A biased oracle in supervised learning is functionally equivalent to the corruption function, C, in a corrupt reward Markov decision process. This is not obvious, but it's true, and I'll expound a little bit briefly with some math next. So then, of course, biased supervised learning is a special case or class of corrupt reward Markov decision processes. And here is our ultimate assumption. This is what we've been building up to this whole time. We can use the fairness condition in observation 3 above, the Lipschitz condition, essentially, as a sufficient condition for our reinforcement learning agent to be able to learn in a corrupt reward Markov decision process, or at least we can use that as a condition of safety in these goal misspecification problems. And if we can use that as a condition of safety, maybe we can use that to find a solution to training these things in a safe way. So this is more for collaborators, future collaborators. So we're going to assume this supervised learning notation setup, a supervised learning task T, curly T, with a solution set capital T that's a subset of the task's feature space and the task's label space. For example, this X could be the set of all possible 28 by 28 black and white images. This Y could be the label of 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the the solution set would then be the set of all black and white images of those numbers. And then this task is then the MNIST task, right? So then we have access to a data set. This is the actual MNIST data set that everyone uses. It's a sample from a distribution over the solution set. And it's a finite sample, right? There's some cardinality on this set n. It's a positive integer. So we're going to make the connection between CRMDPs and supervised learning explicit here. Note that this is a special case of the former. But so we have this state space S in a Markov decision process. That corresponds to the feature space of the solution set. So this is the projection of the solution set over this X component, this first component. Then for your action space, it's essentially the labels, right? It's the label space, the label component of the solution set projected onto, or it's the solution set projected onto the label component. Essentially, it's just the X and the Y, right, in this data set. But it's actually not just the data set. It's with respect to the entire solution set, which includes samples that are not in the data set. So our policy in reinforcement learning is our hypothesis. In supervised learning, we have this notion of an optimal policy, and that's the target function that we try to learn in the supervised learning framework. And we also have this corruption map in CRMDPs. That is going to correspond to the oracle. Not one-to-one, but it's going, not mathematically, it's not exactly the same way, or at least the way that we frame it, it's not going to be the same. But functionally, it's going to do the same thing. It's going to introduce noise into the learning task as follows. In reinforcement learning, we have this true reward. That, in this case, we're going to define it, and it's going to be the probability that the action that we chose is actually the action that an optimal policy would have followed, assuming that it was in that state. And so we're literally just going to swap out the state for the X part of our data point and the action with the Y part of our data point, and now we have the exact same thing. This is the probability that Y follows the target function. And this is actually, if you look at classification, this is actually the exact same optimization objective. We want to maximize the probability that our function, that our hypothesis function, is going to match this optimal target function. Now that I'm looking at this, this notation is probably pretty poor. This should probably be replaced with f of x, and this should probably be replaced with pi of s. But that's okay. Maybe I'll replace that and cut this out or something in the YouTube version. Anyway, when we move on to our observed reward over here, this is the true reward under the corruption map, and it's actually going to be the probability that of an action following the oracle. So this is, instead of following the ground truth or the target function, it's following what the oracle believes is that truth. And again, if we have an optimal oracle, these are the same thing, but if we have a biased oracle, these will be different, and there will be an actual corruption here. So we will be strictly in the corrupt reward setting instead of the normal MDP setting. And then just for kind of, to make this a little bit more concrete, for those who are familiar with reinforcement learning and the formalism there, at the bottom we have these state transitions, right? That's one of the components of a Markov decision process. And the idea here is that the state transitions are actually independent of the action that you took under a generic sampling strategy and under a common sampling strategy, which is complete like random sampling from your data set. It's actually independent of the previous state as well. But in general, we still do have state transitions. They're just independent of our actions or our history. And that's what we're going to assume going forward, is that we're going to assume kind of a a uniform random sampling strategy. So the probability of a state transition for every state in the supervised learning MDP, it's always going to be constant, and it's going to be defined as 1 over the number of points in our data set, in our training set. So there are a couple things that I kind of left out of this. One is the discount factor. Normally people treat that as a hyperparameter of your agent, although formally it is a feature of the Markov decision process. In the supervised learning case, I would say that the discount factor is going to be 1 or 0, depending on how you define it. But in general, we just don't care about anything other than this specific state that we're in. So this still does satisfy the formalism. And additionally, what else? Yeah, I guess I'll move on if I remember. Anyway, again, we're not going to change anything other than this loss function instead of a supervised learning loss function like mean squared error or negative log likelihood or log maximum likelihood or whatever, or the negative likelihood, rather. We're just going to replace that with the policy gradient loss or the Q function loss, depending on whatever reinforcement learning agent. Or we could even think of this as, if we want to do like evolutionary strategies, you could think of this as like the negative of the fitness function or whatever. And then again, this Lipschitz constraint is going to be identical. It's just going to be under this mu here is a policy, but the formalism is going to stay exactly the same, as we'll see. This is that Lipschitz constraint using the notation in the original paper. This is the notation that we're going to go with now. On the supervised learning side, we're essentially just replacing, we're saying that for 2 different data points, the output of our hypothesis function should be similar, assuming that that the input features are, or the input points are similar. If we go on the left here for reinforcement learning, we're saying a similar thing, an identical thing. We're just rephrasing it in the language of reinforcement learning. We have a policy and states instead of a hypothesis and input features. So, what have we actually done here? Well, we've modified the assumption 3 that we talked about before from the original authors. Before, we were assuming that the corruption is finite. Now we're assuming that these distance metrics exist. We're assuming that they're, given a specific measure of statistical distance, we're going to assume that there exists a metric over the input space such that known safe states are similar to other safe states, but dissimilar to corrupt states, right? So we're essentially saying, not necessarily that they're linearly separable, just that, well, I'm not going to go into that, essentially. I haven't quite figured that out yet. But the point is, we're going to satisfy this Lipschitz condition with respect to safe versus corrupt states. We're going to treat safe states as kind of like its own group, and the corrupt states as its own group. And we want those groups to be dissimilar. We want the outputs to be dissimilar because that's where the pattern of our task is. But in general, we also want safe states to be similar to other safe states, regardless of the reward information associated with them. So our problem 1 of this original assumption that it required a finite number of states, that's disappeared. Because we're talking about corruption relative to other states, it doesn't matter how many states there are. It just matters that this condition can hold, that we can find a metric such that all of them satisfy this condition. Number 2, that general quantizing agent was computationally intractable. Here, this is actually computationally feasible when the number of states is small, and then there are approximations that we can consider that are feasible, computationally, but don't require any additional assumptions. It'll just change the bounds. We won't be able to satisfy the same guarantees necessarily, but it may work in practice without introducing any new assumptions about the environment. So in general, what we're doing here, we're not saying that we're essentially, if this similarity measure exists, then we're saying that we can essentially treat the environment as a fairness problem and try to solve it the same way. And that's because the reward information, which is what we care about as far as like the noise goes, that's not trajectory dependent. That is fully observable given the current state information. So the dependence on the history that you see in a Markov decision process does not actually matter in this framework. And again, I don't want to like say that this solution is better, that this assumption is strictly better than the original assumption that the original authors made. It's probably not, right? We can imagine situations where this similarity measure doesn't exist, but there is finite corruption, and so the methods of the general quantizing agent would hold. But there are also probably situations where, as I've demonstrated here, right, this doesn't require a finite number of states. So there are automatically, I guess, assuming that this is learnable, there would be environments that are not captured under these assumptions that are captured under these assumptions. And so this is all about expanding the class of known solvable corrupt reward Markov decision processes. So next steps, of course, we need to prove that these are actually learnable under this new assumption, which is not trivial. And we'd also like to see some grid world experiments demonstrating on some simple grid worlds that Lipschitz-constrained reinforcement learning agents can learn in these corrupt reward environments, perhaps using this repository that I've been working on for quite a few months now. Well, on and off. And then a future work that I see from this just right away, not having even worked on this paper completely and like finished, is that similarity metric. So currently, like, that needs to be defined, right? Just because it exists doesn't mean that we have access to it, and we would need access to it in order to solve agents this way, or solve these environments with current RL agents, at least, using that constrained optimization that we talked about. So the hope is that when that similarity metric exists but is hard to determine or hard to define analytically, that we could potentially learn that similarity metric, maybe using human feedback in some way, or perhaps transferring from an unsupervised approach or something, maybe using a model of the environment. So those are the next steps. In conclusion, what are the research implications here? The larger research implications, I guess, that fairness and bias problems are actually goal misspecification problems in disguise. That technical fairness research and technical AI safety research should actually be considered jointly. In particular, this kind of debate that happens between fairness researchers and kind of long-term AI safety researchers. This debate that they have around priority, whose research field should be prioritized, it's actually kind of a false dichotomy. They're arguing about the same fundamental problem because results in one field can be repurposed for the other in this specific context. And in general, I think this should be done more often in general, like supervised learning and reinforcement learning. Those two fields, I think they do draw inspiration from each other, but they don't cite it often enough. Anyway, broader conclusions. This was for like kind of the high-level audience that's not familiar with some of this research. AI will not be beneficial to society by default. Artificial systems designed with biomimicry can fail in all the same ways that their biological counterparts do, which I think was something that for people at the conference was not always obvious or apparent. These failings that we're talking about already impact society at large and will do so increasingly at scale without active prevention as we deploy this technology more and more. And technical solutions to these problems exist, or maybe too relaxed versions of the problems, right? We talked about fairness, and that's not always solvable technically. But in safety, maybe that is the case. But the problem now is that these solutions are not often surrounded by governance and good governance in strategy, policy, and engineering. For example, all this work on fairness and training fair classifiers, that was all around, that paper was published, I think, in 2011. And all those systems that we talked about before, those were all systems that were designed and deployed after that paper came out. So obviously we have a long way to go as far as deploying these solutions in the real world. And again, I meant to stress this earlier. Google's not the only one that's deploying faulty machine learning systems. I just picked on them because they're the easiest to pick on in the sense that they touch the most people, and their systems are the ones that are known to do this because everyone uses Google. But in general, Facebook, Microsoft, Baidu, all these large companies that are doing machine learning, they all have this problem, and they all deal with it or don't deal with it more often than not. And even Microsoft, I think, is the only one that really has acknowledged this as being a problem, like vocally, and to the point, at least to the point where they've come out and said that they need regulation, that they believe they need to be regulated externally, that they can't do it themselves. And I think that's true of all these organizations, personally. But that's pretty much it. Thank you for tuning in. If you are one of the researchers that I made this video for, that will be working on this in prog together, hopefully by now you've had a chance to read these papers and to just watch this presentation. Hopefully it makes a little bit more sense because the blog post that I shared was not very well done, or at least it wasn't perfected or made presentable in the same way that this presentation was. And so hopefully we're all on the same page at this point, and so when we have future calls, we can start planning how we're actually going to do this. Thanks for watching, everyone. See you next time.